Look down. What do you see? Dirt? Sand? Rock? You're looking at the silent, unsung hero of our modern age. You're looking at silicon. It's the second most abundant element in Earth's crust, right after oxygen. Every grain of sand on a beach, every piece of quartz sparkling in a riverbed is packed with it. This common, everyday stuff is the raw material for our entire digital civilization. It's a cosmic irony, really. The very substance we walk on, the dust we sweep away, holds the potential for the most complex machines humanity has ever conceived. From the ground beneath your feet to the stars we map with supercomputers, the journey begins with this humble dust. Think about the sheer scale of it. So how do we begin this epic transformation? We start by digging. Quartz sand, rich in silicon dioxide, we get it hot. Really hot. Into a massive electric arc furnace, cranked to around 2000 degrees Celsius. Carbon is introduced to the furnace. Oxygen atoms bond with carbon, leaving silicon behind. Carbon monoxide gas floats away. Left over is metallurgical-grade silicon, messy, about 99% pure, fine for aluminum alloys. For electronics, not even close. Computing needs near-impossible purity. A single misplaced atom in a billion can ruin everything. Raw silicon enters chemical purification, converted into trichlorosilane gas, purified via distillation, again and again. Ultra-pure gas is decomposed over a hot silicon rod. Silicon deposits layer by layer, forming polysilicon rods. Now we have our perfect silicon ingot, a monument to purity. What's next? We slice it. Diamond-tipped saws cut the ingot into ultra-thin discs. Each disc is a perfect circle called a wafer. Wafers are polished flatter and smoother than any mirror, down to atomic scale imperfections. This pristine surface is our canvas. Here we will etch the intricate patterns of thought itself. Photolithography, like advanced photography or screen printing. But at a scale smaller than a virus, the wafer is coated with light-sensitive photoresist. A mask, a stencil blueprint for one circuit layer, is placed over the wafer. Ultraviolet light shines through the mask onto the photoresist. The light causes a chemical change where it hits. The wafer is developed. Exposed or unexposed photoresist is washed away. A precise pattern remains on the silicon surface. That pattern protects some areas and exposes others. Now the real sculpting begins. The exposed silicon is bombarded with superheated gases, a process called doping. Phosphorus is introduced. Boron is introduced. Why add impurities? So we have the chip, a beautiful complex sculpture of silicon, copper. But how does it, think? How does this inert object perform calculations? Store memories? Render graphics? The secret isn't in the silicon itself, but in the mathematics we've embedded within its structure. The chip's power comes from a beautifully simple idea: the binary system. Every one of those billions of transistors is just a switch. It can be on, or it can be off. We assign a value to each state. On is 1. Off is 0. That's it. The entire, rich, complex digital world is built from just those two numbers. This seems impossibly simple, doesn't it? How can you represent the color red, the sound of a symphony, the words of this essay, with just ones and zeros? The magic is in the patterns. A single switch, a single bit of information, can't tell you much. But what about 8 of them in a row? Now let's scale up. If a single computer chip is a brilliant solo musician, think of a supercomputer as a world-class orchestra. Thousands, even millions of musicians playing in perfect harmony. A supercomputer isn't just one giant fast chip. It's a massive collection of processors, all working together on the same problem. The challenge here is not just speed, but coordination. How do you get millions of processors to cooperate without tripping over each other? The answer is hidden mathematics, sophisticated algorithms that govern this symphony of calculation. Imagine trying to predict the weather. You have to model the entire atmosphere. Temperature, pressure, humidity, wind speed at millions of points across the globe. A single processor would take centuries, but a supercomputer can divide the problem up. One group of processors might calculate North America, another the Pacific Ocean, another the stratosphere.